Hello. This video is for Math 261, Applied Calculus 1, Section 2.6, and in this video I want to go over the two application problems that you will see on your homework, and I do plan on putting one of these on your exam too. So please watch this video, take notes, and even though I don't have a classwork problem that I want you to submit on Canvas, you will see them on your My Math Lab homework this week. I did put a blank PDF, a copy of this on Canvas if you want to print it out and work on them. The blank one is available there. So it's got example number 1, A through E, and number 2. And these are really just from your homework. I felt like I didn't really have anything like this on the notes that we went over because we just really found the derivative a whole bunch of times. Didn't really do an application problem. So let's do this one together, okay? So the population of Neelam doubles in size. So take a look. We have a population that doubles in size. If you were to write an exponential function for doubling, just real quick, say that you have 1 initially, and if you double you get 2, and then the next one will be 4, and then it will get what, 8, and then 16, and dot dot dot. It's growing pretty quickly, right? But if you are trying to write this as an exponential form, well, 1 is 2 to the 0 power, 2 is 2 to the first power, and 2 is 2 squared, 8 is 2 cubed, and 2 to the 4th, and so on. So whenever we have a case like this that's doubling, the base of our exponential will be 2. And I guess I'll just put x here. But depending on the input variable, it looks like they're using t, so I'll just put t for right now, but we have to keep on reading because it's gonna be more than that. But say that if it was, let's say, what if it was like the word is triple, then then your base is not going to be 2 but more like 3 to the tth power, or so on. You see what I mean? Just wanted to talk about that the base is going to be 2 here, and it's not doubling every year, but it's doubling every 5 years, right? So starting in 1990, and back in 1990 its population was 15,000. Okay, so we're going to use that as our initial population, and we'll say t equals 0 is 1990, okay? Okay, let's read part A. Find an exponential function of the form p of t equals p naught times n raised to the little t over big T. Now this will be given to you on your homework too, but we could have written something like that on our own, but let's keep it. That models Neelam's population after t years. And I gave you a little note here. If a population or quantity doubles in t units of time, and we know what this big T is. Big T is 5, and how do we know that? Because they did say it's doubling in every 5 years. So our big T is 5 years. Then after the little t units of time, and that little t is going to be, it can be 1 year, 2 year, 3 year. That's our input. It's going to change. But what if little t is, I'm just making up a random number. What if little t is 15 years? Then how many times did our population double? That's going to be little t over big T. So 15 over the 5. So our population would have been doubled 3 times in 15 years. So that's where this little t over big T came from. And as you can see where that come from, where that came from. So let's go ahead and write that equation. So P of t equals, now P naught, that's the initial population. We know that is 15,000 times, now n, what is the base of this exponential? Now this is doubling every time, so little n is 2 raised to the, little t is the input, so I'll keep the little t, but big T is how long it takes for this population to double. So that will be the equation that they want. That will be the equation that they want. And that's my answer for part A. Okay. All right. Let's keep going and let's look at B now. Find the equivalent exponential function of the form P of t equals P naught times e raised to the RT power. Now, it looks almost the same, but you notice they want us to rewrite it so that the base of this exponential is not 2, but e. And they want you to round to 4 decimal places as needed. Okay, so I need to change my base. The base was 2, but I need to change this 2 to e, right? All right, so let's try that. So P of t equals, now P naught stays the same, still 15,000 times, but how can I rewrite 2 so that the base is e? And remember, this is a little trick that I used in, I think, the second video when we were trying to find the derivative of a to the x power using the derivative of e to the anything. So I'm going to rewrite 2 as this, okay? See if you agree with me. I'm going to rewrite it so that 2 is e raised to the natural log of 2. Oh, how fun, right? I'll keep that t over 5. But hold on. Let's see if you agree with me, okay? You agree that this e raised to the natural log of 2, that just equals 2, right? So that's okay. That's what I did. That's what I just did. I rewrote 2 so that it has e as the base. Now I'm going to go ahead and simplify this, okay? So P of t equals 15,000 times e raised to the, now take a look. I'm going to go ahead and highlight the constants or the numbers here, okay? You see what I'm just circling? I'm going to go ahead and write that as a separate fraction. Natural log of 2 over what number? 5, right? Times my variable t. And this is where we're going to have to round to 4 decimal places. So I'll get my calculator over here. I did get an email that TI, Texas Instrument, they're going to let us use their software for free for the next 6 months. So go check it out. I may post that link on Canvas too, so that you can download like a graphing calculator or a scientific calculator if you don't have one, but I think you all have it. But anyways, I typed natural log of 2 over 5 in my calculator, and I got 0.1386. So I'm going to write my final answer. P of t equals 15,000 times e raised to the 0.1386 t. And that's it. And that is it. That is the exponential model with base e. Okay. Let me highlight something real quick here. What does this stand for, guys? This number that we just found. That is the R value, right? That is the rate. That is the growth rate, and that's what they are asking you to find on part C. What is Neelam's yearly percentage of growth rate. And they want you to this time round to 2 decimal places. So I'm just going to use that number 0.1386, and I'm going to just multiply that by 100. So what is the yearly percentage of growth rate? 13.86%. Okay. All right, doing good. And you know, when I write a model, I want to use it, but it says on D, without using your calculator, What am I doing here, guys? Sorry. Without using a calculator, find Neelam's population in 2005. So, 2005, what's the T going to be? T is going to be 2005 minus our initial year, 1990. What's that going to be? T equals 15 years, right? So they're asking you in 15 years, how many people will be in Neelam? And I think this one is what I kind of used up here in A to explain that little t over t. But notice that they said this population doubles in size every 5 years, right? So in 1990, there were how many people? 15,000. That was given to us. In 1995, 5 years later, we double this amount. We're gonna have what? 30,000 people, right? Let's keep going. In what's the next number? In the year 2000, we're gonna have 60,000 people. I simply double the previous population. And finally, 5 years later, in 2005, we're gonna have how many? 120,000 people. And that is the answer that we can find without using a calculator, just doubling to 3 times. And if you doubling our original population 3 times. So this is what we did. We really did 15,000 times 2 raised to the 15 divided by 5. So we did 15,000 times 2 to the 3rd power. And that 3 means we doubled the population, the original population, 3 times. So I just did it in that list, but the answer that we want to give them is that Neelam would have had 120,000 people. Okay? All right, let's look at the very last one. How fast was Neelam's population changing in 2005? Now this is the derivative. This is where we need to use the calculus, right? So which one do you want to take the derivative of? We have 2 different models. We have 2 models. They are equivalent. So it doesn't matter which one we differentiate. But because we just did a lesson on differentiating an exponential function with base other than something other than e, I think I'm going to go ahead and differentiate this little guy. Okay, so take a look. Let me just bring this down a little bit. P of t equals 15,000 times 2 to the t over 5. I am going to find p prime of t, and then we're going to plug in t equals 15 in there. Okay, that's our plan, okay? So let's differentiate this. It's going to be 15,000 times the derivative of d dt 2 raised to the, I'll write it as 1 over 5t power, okay? Same thing, right? Keep going. P prime of t is this 15,000 times, remember how to take the derivative of this expression right here, right? Let me use a different color or something like that. Okay, that will be, we need, natural log of 2, we need that, multiply by the original expression. But remember, we need to use the chain rule here. So take the derivative of d dt of 1 over 5t. So finally, I'm just going to bring this all the way up. Finally, p prime of t, oh, not finally yet, 15,000 times ln2 times 2 to the 1/5 t times, and take the derivative of this 1/5 t. That's just gonna be 1 over 5, right? Okay. Oh, we can simplify this. We can simplify this 15,000 divided by 5. So, but is that, I think that's it. 15,000 divided by 5 is gonna give us 3,000. So my final p prime of t is, let me write it as 3,000 times natural log of 2 times 2 to the 1 over 5, 1 over 5th t. All right, what were we planning on plugging in to this derivative function? Remember, it was t equals 15, right? We got 15 from doing 2005 minus our base year of, what was it, 1990? Oh, I think I wrote a number that's way too big. 2005 minus 1990, I believe. Yep. So we got t equals 15. So let's plug in t equals 15 into our derivative function. 3,000 times natural log of 2 times 2 times 1/5 of 15. Just going to be 3 right there. So I'm typing this in my calculator, guys. 3,000 times natural log of 2 times 2 to the 8th of, sorry, 2 to the 3rd power. That will be 16,635.5. So let me round that up to 636 people per year. So it was growing. Oh, in what year? In 2005. So Neelam's population was growing. It's a positive number. It's growing 16,636 people per year in 2005. Okay, and if we have time, well, we have time, but if I have more room, I wish I had more room. I wanted to take the derivative of the e expression, this one right here, you see? And then plug in 15. We better get the same thing, but I may try that after stopping the video, okay? All right, but that's what I want you to try. Just because we talked about finding the derivative of an expression that has base something other than e. So do try this method on your homework, okay? All right, let's look at example 2. This one's a little bit shorter though. Okay, the intensity of a sound is given by I equals I naught times 10 raised to the 0.1 times L, where L is the loudness of the sound as measured in decibels, and I naught is the minimum intensity detectable by the human ear. Find I in terms of I naught for the loudness of a garbage disposal. Is pretty loud, which is 80 decibels. I'm not sure if I'm reading this right. Decibels. Decibel. Okay, so I equals, you guys, we're given L here. This is our L. This is how loud. This is the loudness of the sound. L equals 80. So let's plug in everything we know. I equals I naught. I don't know what that is. They never gave it to us. Times 10 raised to the 0.1 times 80. Now let's simplify that. I equals I naught times 10 raised to the 8. Okay, and that's it. That's what they wanted. We found them. That's it. All right, what about the second one? Find I in terms of I naught for the loudness of a mosquito. Oh, a tiny mosquito, pretty quiet, which is 20 decibels. I looked these random things up on Google. But because the example that you're gonna get on the whole homework, I think it's like effect. I don't know. Like you'll see something else, but pretty quiet mosquito. I equals I naught times 10 raised to the 0.1 times. What's my L this time? Our L this time is 20. So if I simplify this, I will get I naught times 10 to the second power. Okay, so that's gonna be the intensity of a mosquito sound. Am I reading this right? The intensity of a sound. Yep. All right. So we found these two expressions. I circled them. Let's look at the very last. Well, not last one. C. Compare your answer to part A and B. Fill in the blanks. All right. Let's compare these two. The first one I have is I naught times 10 to the 8th power. And the second one I have is I naught times 10 to the second power. So let's compare these two. This one was the garbage disposal. Oh, I'm enjoying writing on this pad. Oh, and this one was our little mosquito. If I'm comparing them, I notice they got something in common. I naughts, bye-bye. And I'm going to divide 10 to the 8th by 10 squared. And what's that going to be? That's just going to be 10 to the 6th power. Okay, by subtracting the exponents, 8 minus 2, we get 6. So the garbage disposal is 10 to the 6 times louder than the mosquito. That's good. Wow, very loud. All right, now let's do some calculus. They want you to find the rate of change, di, dl. I'm going to go ahead and copy down our equation. I equals I naught times 10 raised to the 0.1 L. Okay, so what do they want? They want the derivative of this. So di, dl, the derivative of the intensity with respect to the loudness is equal to I naught is the constant, so just write it down. But we're going to need to find the DDL of 10 raised to the 0.1 L. Okay, so what's that going to be? I naught times this guy right here. This is an exponential expression, so you will need your natural log of 10 times that same expression, 10 times 0.1 L, and use the chain rule to find the derivative of the exponent. I'll just write it as 0.1. And where did I get 0.1 from? Because DDL of 0.1 L is 0.1. Okay, let's simplify this now. If I simplify this, I'll get I naught. Is there anything to simplify really? Not really. There's nothing I can really multiply here. So do I want to change the order a little bit? I think that's fine, but if you really want to write it as 0.1 I naught times ln 10 times 10 to the 0.1 L. I guess that's fine. I guess that's good. Well, we found it. We found the derivative or the rate of change, di over dl, and that's what it is. Okay. Well, I wanted to know what the I naught is. They just never told us. Okay. Let's interpret the meaning of this didl. Didl is the rate of change, right? That's the rate of change of the I intensity of the sound based upon its, what was the letter in the bottom? L. It's L, what? Loudness. Okay. And that is it. We did everything for this example. It just created a random third page. I don't need the third page. But I'm going to go ahead and scan this on Canvas and also post this in addition to the video. Some random parts. But that's it for 2.6. And that is really it for chapter 2 too. We'll talk about if I want to test you on just chapter 2 or wait until the end of chapter 3. But, well, thank you for watching all 3 videos this week. I look forward to checking your classworks on Canvas and have fun working on your Math Lab homeworks. But do email me. Email me in case you want to have like a virtual office hour. Oh, go away. Oh my gosh, why is it? Oh, maybe I'm not allowed to write there. You know my email address, but some people were writing using the wrong email. It's not VCCS, it's nvcc.edu, okay? So email me if you want to have a Zoom conference. I look forward to hearing from you. Thank you.